Thank you very much for inviting me to give this talk. It's a pleasure to be here participating in such an interesting workshop. Today, I'll be talking a little bit about this concept that we recently put forward called the value equivalence principle. And this is joint work with all these great collaborators whose names you can see on the slide. And I have to say that Chris Green was the one who did actually most of the work. To start motivating the value equivalence principle, I thought that maybe a good place to start would be to discuss what exactly I mean by a model, because the concept of model changes a little bit from context to context. So for the purpose of this talk, a model will be a function, or you can think of it as a black box that takes in a state and an action and spits out a next state and a reward. And so, for example, if we're doing something like Atari, the input could be a frame or maybe a sequence of frames. The action would be some command coming from the joystick, and then the model would ingest these things, these objects, and would spit out, for example, the next frame and the points associated with that transition. And as we all know, in reinforcement learning, we do not assume the agent has access to the model. So if we want to use the model, we have to learn that model. So for example, for concreteness, we can think of this model as being a neural network, and then we have to train that neural network to act as a model. So the talk today is going to be about effective ways of learning a model. So the motivation for the value equivalence principle is that at some point we will need, or the agent, RL agent, or more generally an AI agent, will have to ignore some aspects of the environment. So these days we can actually have pretty big neural networks or even other approximators, but at some point, as we tackle more and more complex problems, at some point, because the world is a complex place, at some point the agent won't be able to represent everything. And then at that point, the agent will have to compromise. And not all compromises are equally good. So what do I mean by that? So for example, let's say we're dealing with a race game, and let's assume that the agent doesn't have enough representational capacity to compute the perfect model of the environment. So one solution would be to compute a model that only looks at half of the screen, which is clearly not a good solution, because relevant information is being lost. So if we use this model for planning, probably the resulting policy wouldn't be great. But if instead, if we removed the background, we're handling less information than if we were to consider everything. But in this case, we would probably be able to plan pretty well, maybe even optimally. So in general, this is of course a very simplified, intuitive way of posing the problem. But our main argument is that if we want to be able to do something like this, if we want to be able to find the right compromises when learning a model, we should take into account how the model will be used when we're learning the model. And this may come across as an obvious statement, but in reality, most of the conventional model learning techniques do not do that. So this takes us to the value equivalence principle. What is it? The value equivalence principle is a formalism that allows us to set this trade-off, allows the RL agent to define the compromises in the model in the specific case in which the model will be used for value-based planning. So what do I mean by that? As we know, in most of value-based RL algorithms can be understood as approximations of these dynamic programming's basic loop, which alternates between two operations: policy evaluation, which is the computation of a policy's value function, and policy improvement, which is the computation of improved policy based on a value function. Now, the assumption here is that we will be using a model to do policy evaluation. So given a policy, we will compute the value function of that policy using a model. And one way of formalizing this is to define the Bellman operator, which is whose definition is on the slide, the Bellman operator associated with a given policy. The details of this definition doesn't matter much at the level of this talk. The only thing I want to point out is that if we fix the state space and the action space, the only thing that changes when we move from one environment to the other are two objects, P and R. So P is the transition kernel, or the transition probabilities between states given an action, and the reward function R, which gives us the expected reward associated with the execution of an action in a given state. So for this talk, a model will be a tuple composed of these two objects, R, the reward function, and P, the transition probability function. So now, equipped with this concept, I can introduce the value equivalence or VE principle. So a VE principle says the following: giving a model M, if we pair it up with a policy pi, an arbitrary policy pi, that gives rise to the Bellman operator T pi. Now, if we plug in any function V and we apply this operator T pi to V, we get a new function V prime. Now, suppose that we have an approximation of M given by M tilde. If we pair up M tilde with the same policy pi, this pair will give rise to an approximation of T pi, which is T pi tilde. Now, if we plug in the same function V and apply T pi tilde to V, we get V prime tilde. So what the VE principle says is that M and M tilde will be value equivalent, or VE, with respect to pi and V, if V prime and V prime tilde are the same object, are the same function. And of course, we can generalize this to more than one policy, in which case we would request that for any policy we pick from this class, from this set of policies big pi, any policy pi that we plug in, this relation would hold. And the same with a set of functions big V. Again, any function that we plug in, the relation should hold. So now that we have this concept, we could define a minimization problem, which is what gives us a model. So essentially what we do here is for each policy in pi and each V in each function in V, we minimize distance between V prime and V prime tilde. So in some sense, this is connecting with the motivation. What this gives us is a sort of language to tell the agent what is it that we care about. So depending on the choices of big pi and big V, the set of policies and the set of functions, we are essentially telling the agent what to pay attention to. And this, of course, invites the question of how to define these sets in practice. So at the end of this talk, I'll give you a pointer to the papers where we discuss these things in detail. But for now, I'll just ask you to believe me that when there is a finite number of actions, we can easily define the set big pi by just having one policy associated with each action, and that policy simply picks that action across the entire state space. So I'll consider that the problem of solving defining big pi is solved for now, and we'll focus on the problem of how to define the set V. So how do we define the set V? So to answer that question, I'll start by pointing out a property of V, which is interesting. Suppose that we start with a set of functions V prime prime, and we start with a space of possible models M, big M. Now, if we apply the V principle to this class V prime prime, that defines a space of models, which we denote by MV prime prime, that are V with respect to the set. So any model in this class will have the right effect on the functions in V prime prime. Now, if we replace V prime prime with another set of functions, V prime, which is a superset of V prime prime, and we do the same exercise, we end up with a new class of V models, MV prime, which is smaller than the original one, which is sort of intuitive if we think about it. And if we keep doing that, we keep getting smaller and smaller VE sets. In the limit, when we have all possible functions in V, we have one of the two situations. If the true model, a model that represents the environment perfectly, belongs to the space M, then we end up with a singleton of a set with a single model that is the exact model. Otherwise, if this model doesn't belong to M, then we end up with an empty set. Okay, so that's interesting, but how does that help us to define V in practice? So to answer that question, I'll point out a second property of V, which says the following. If a model M is V with respect to a set of functions V, it will also be V with respect to any linear combinations of these functions. What that means is that if you want to be V with respect to a set of functions, we only have to be V with respect to a basis of that set. Now, how can we use it in practice? So in practice, the agent always has two objects. It has a model, at least two objects. A model-based RL agent will have a model, and it will have a way of representing value functions, a function approximator. So let's assume for concreteness that this is a neural network. Now, from the agent's perspective, it only makes sense to be V with respect to the functions it can represent. If there's a function that is beyond the space of things the agent can represent, being V with respect to that, it doesn't matter, right? So, for example, in the concrete case where the value functions are represented by neural networks, the space of things, of functions the agent can represent, would be all possible instantiations of this neural network. And this is the space that matters to the agent, which in turn defines the set of functions used for VE. Now, as I said, we only connecting now with the previous, well, as I said, we only need to be V with respect to a basis of this space. So we can see two cases. If the approximator happens to be linear, then in that case, we know that the space of things the agent can represent is the space of all possible linear combinations of a fixed set of features. So in that case, the features themselves can be the functions used for V. So when we have a linear function approximator, we have a very easy way to define the function V. The space of functions big V. In the more general case where the value functions are represented by nonlinear approximators, then we need to find a basis for this space. One way of doing that in practice is to sample from this space, and if we sample enough of these models, we might spawn a big subset of this space. And I'll now discuss experiments in which we did exactly that. So for the experiments, we use these two domains, catch and cart pole. These are pretty traditional domains in RL, so I'll assume that most people know what they are. So I'm not going to describe them. What I will describe, though, is how we actually carried it out, the experiment. So what we did was the following. We first took a random policy. We collected data using a random policy. Now, using the same data, we computed two models. A conventional model based on maximum likelihood estimation, and a V model, value equivalent model. Now we use the model to compute the policy, so solved the model, and then now we evaluate the model on the true environment. So what I'll show you now is the performance of the policies computed by the two types of models when they are executed in the real environment. So I'll show you a number of plots that all have essentially the same structure. So let me try to break this one down first, and then I'll show you the others. So here we see two curves, one in red and one black. The red one is value equivalence. The other one is maximum likelihood estimation. On the plot here, on the y-axis, we see the average state value, which can be understood as a measure of the performance of the resulting policy. On the x-axis, we see a measure of the capacity of the model used by the agent. So as I said before, the agent has two things. It has two objects. it holds a model and holds a value function approximator. In this case, the model is a tabular model, so it's a set of matrices and a set of vectors. And what we did was to constrain the rank of the models as a way of controlling the capacity of the model. And for function approximator, we use state aggregation. And because this is a linear model, we can very easily define the set V used by V by just using the features, or in this case, the clusters, as the functions V used for V. So now what we did was we fixed the approximator, we fixed the number of clusters in the state aggregation, and we varied the capacity of the model, the rank of the matrices used to represent the transition matrices. And you see that when both approaches have enough capacity, then they do pretty much the same. But as we restrict the capacity of the model, we see that VE does considerably better than MLE. And the reason for that is because the model computed by VE takes into account the things that the agent can actually represent, namely the functions V. We also did the opposite, meaning in this case, now we fixed the model, with a given capacity, and now we changed the number of clusters using for state aggregation, which also for the VE case, also defines the functions used for VE. And again, we can see that VE does better than MLE all across. We also have analogous results for cartpole, because in this case, we have a continuous state space, then both the model and the value functions are represented by neural networks. And the way we computed the set V in this case was to sample from the possible instantiations of the value function neural network. And again, you can see here that the V model does in general better than the MLE counterpart. So this is only a small subset of the experiments we have. You can take a look at the paper to see many more experiments, but the general takeaway is that in general, VE does considerably better than MLE, especially under capacity constraints. Okay, so this was an overview of the concept of value equivalence, but then recently we proposed a new concept which takes this idea one step further, which we call proper value equivalence, which I'll quickly present now. So the idea here, so as I said before, in VE, we have this interesting property that as we increase the number of functions that are taken into account, the resulting VE set, the resulting set of models that we consider to be acceptable shrinks. So this gives rise to a trade-off. On one hand, we want the VE class to be as big as possible, because it's much easier if the class of acceptable models is bigger, it should be much easier to find a model in that space. On the other hand, depending on how we define the set V, some of the models in the resulting VE class might actually not be good to plan with. So just to illustrate, think of the extreme case. If we only take one function to be V, so big V will be just one function, probably the resulting V set will be pretty big. But also probably many, if not most, models in this space will not be good for planning. So we always have this tension that we want to have the V class to be as large as possible, but we also want every single model in that class to be good for planning. So the question we ask is, what if we can do both? What if instead of having to trade these things off, what if we can have both at the same time? And this is what proper VE gives us. So to introduce proper VE, proper value equivalence, first I have to generalize the concept of VE slightly. So, and we do this with the concept of order K VE, order K value equivalence. So it's pretty much the same thing. This is exactly the definition I gave before with the diagram. But now, instead of looking at one application of the Bellman operator, we have K applications of this operator. Now, What's interesting about this is that if, for example, we replace order 1V, which is the original one, with order 2V, we end up with a set that is a superset of the original one. So we're increasing the size of the models. More generally, given two integers, small k and big K, the induced order K models will be the order small k class will be a subset of the order big K V class. So one way of roughly what this means is that as we increase K, the order of V, we get larger and larger V classes, which is sort of what we want. And naturally, this invites the question, okay, what happens in the limit, right? So on one extreme, if we take K to be 1, we cover the original V, meaning that the concept of order KV is a strict generalization of the original concept. But if we take it to, what happens if we take it to K to infinity? So what happens is that if you look at the definition at the top, when we take, so K is the number of times the Bellman operator is applied. So if we take it to infinity, what that means is that it doesn't matter which function we started with, we'll always end up with a value function. So then what happened, the result of that is that the notion of a set of functions disappears. So instead, we have now only this the notion of a set of policies and the associated value functions. And this is what we call proper value equivalence. So just to be very clear, in proper value equivalence, we only define a set of policies and we ask the models the only thing we ask from the models is that the fixed points associated with those policies, the value functions of those policies, are the actual value functions of those policies. So if we go back to the topology of this space of order K value equivalent models, it's very easy to show that the M infinity, what we call the proper value equivalence space, is the largest among all the spaces. So this is good. That's one of the things we wanted. But what about the second thing? Because we also want all these models to be good for planning. And it's also not difficult to show that if we have a M infinity model induced by all possible policies, in fact, induced by a basis of the space of policies, where the notion of basis here is well defined, then any model in this space allows for optimal planning. Okay, so why again do we need a large V set? As I said at the beginning of this talk, one thing that we could do when we have a model with limited capacity is to remove some of the irrelevant details from the environment. But another way of thinking about this is that we can just ignore those details, which means essentially that in this example with the car racing, we could have any background, and in principle, planning with any of these models would yield the same policy. And in this case, probably an optimal policy. So we argue that with proper value equivalence, or PVE, we get exactly that property. And we actually run some experiments to illustrate that point. So one of the experiments we ran was in the classical forums environment. And here, this is a stochastic version of the environment. And what we did here was we computed an optimal policy that goes from the red dot to the green square. And we run it several times. And these are the trajectories of this policy. Now, what we did was to take the exact same policy. We pick one PVE model, a PVE set, unlike the original VE that collapsed to a single point. The PVE never collapses. So we have a cloud of possible models. We pick one of them, and now we run the policy on the same on that model, and we end up with this interesting behavior that, as you can see here with the diagonal lines, some of the transitions that the policy performs here in the model are actually not allowed in the true environment. So the environment, and we have many of, if you pick other models, we'll have different transitions. So the model doesn't represent the environment exactly, But yet, if we use this model to plan, and if we compute, and we will end up with one of the optimal policies in the true environment. We run another experiment to illustrate the same fact, which was to compute a set of order k VE models for different values of k. So in this case here, what we did was to initialize 120 models and then monitor these models across training. So here the color represents the stage of training. Blue is at the beginning of training, yellow is at the end of training. So if we compute a VE, order 1 VE, then as predicted by theory, we end up with a single point, the yellow point, because all the models collapse to the same point. Now, if we do the same thing with a VE of higher order, instead of ending up with a single point, we end up with a cloud of points. And if we increase it even further, then we get an even bigger cloud. And if we take it to the limit, namely M infinity or PVE, we end up with the largest possible cloud. So what this means is that if we were to solve this problem and we adopted PVE, then any model here in yellow would be enough for optimal planning. So it's much easier to find a model in this space than it is to find a model in the other one VE space. And just maybe something I should have mentioned, these models here are represented as vectors. We compute the principal components of these vectors and we project them onto a 2D space to visualize things. Details in the paper, I'm happy to clarify after the talk as well. So one last experiment, we also tried PVE at scale. And what I mean by that is that we combined PVE with mu0. And as I said in the beginning of the talk, most of value-based RL algorithms can be understood as approximating dynamic programming, the alternation between policy evaluation and policy improvement. And mu0 can also be understood this way. And if we do cast mu0 in these terms, and we can understand mu0 as computing a PVE model using only the most recent policy as the set of policies. So what we did was, okay, what if instead of using only the most recent policy, if we use the entire history of policies to induce PVE? And we just did that small modification to mu0, and we run it on Atari. So these are the results we got. So here in orange, we see the original mu0 as a baseline. The y-axis here is the median human normalized score across all Atari games. So this is statistics over all 57 games. And on the x-axis, we see the number of frames or transitions used for learning. And you see in blue, mu0 combined with PVE. And we see that there is a small but consistent benefit in using PVE in this case. And I just want to point out that this is perhaps the most direct and naive way of using PVE in this case, but only by doing that, we already get some improvement. I think this is most of what I wanted to tell you guys about today. I just want to show these references. The first two papers are the value equivalence papers that were used as the basis for this talk. There's also a very related concept in the literature called value-aware model learning, which is very related and, in my opinion, complementary to what I just presented today. So it's worth taking a look as well if you're interested in this sort of thing. Thank you very much. That's all for today.